Three, two, one, go. Hey, my name is Mlaba, and today I'll be presenting the project that I was working on. So the purpose of this project was to answer this question: Can you put creatures with tiny, simple, random configured brain in a complex world, give them a criteria for survival, and see smart behavior emerge? So this project was inspired by uh, a guy on YouTube who built this project where he had simple creatures he built, and he never really told them what to do, but because he gave them a criteria for survival, and he put them in a complex world, and over time they learned how to survive, and then they evolved. So I had about 15 hours to finish this project, and it was inspired by the hackathon I just recently attended when I realized that you can actually do a lot in a short period of time. So I challenged myself to do this in about 15 hours. And so here's the demo for the project. So when I start my simulation, this what you see these creatures moving around in all random direction and in all random positions. And this is just because of their randomly configured brain that makes them move this way. And about after 100 simulation rounds, I kill about half of them, and then I use the survivors to as parents to restart the simulation. And I ran this about 100 times. Um, so as you can see, the survival rate did improve a little bit, but it didn't really improve that much. Even after 100 simulation rounds, it doesn't improve. So they don't get really any smarter, but we can explore why that is. So let's look at the brain anatomy of our creatures. As you can see, they have some sensory input where they have some internal inputs. So those includes input that tells you about the internal state of the creature, and then you have external input that, that includes things that tells you about um, the world within the vicinity of the creature. And sensory input are connected to internal neurons, which are usually connected to output or action neurons. Those also could be categorized into two categories where you have internal output and external output. Internal output tells you about internal output changes the internal state of the creature, external output changes the world in one way or another. So those things that include movement and sometimes killing other creatures and all those kind of things. And so internal neurons are the ones that took me quite a bit to understand. I still don't understand them very well, but what I can tell from what I understand is that the more internal neurons you have, the more layers you have in your brain. And the more layers you have in your brain, the deeper your creatures could think. And internal neurons can connect to each other, or they can connect to output neurons, but they can also connect to themselves, creating some kind of short-term memory. And so a gene is made of two neurons where you have a source and a sink, and a source can be an input or internal neuron, which has an output value of -1 to 1, and then you have a sink neuron, which could be either an output or internal neuron, and then you have a weighted connection, and the weight is usually a value between -4 and 4. So this value is randomly generated at the beginning of the simulation. And a genome is just a bunch of genes, and let's look at an example brain to see how I go ahead and calculate the output of each creature. So this is a brain with sensory input A, B, and C, and then you have internal neurons X and Y, and then you have output neurons. You have 1, 2, and 3. And as you can see, it uses only one sensory input, and it has three output neurons connected. So that means this creature can perform all of these three actions. And so in our sensory input, it has a value that was calculated during the simulation round of 0.63, and is connected to an internal neuron X. It's also connected to an output neuron 3, and so this X is connected to 1 and 2, and then you have these values which they are the weighted connections. And how I calculate the output of each neuron is I take the sum of all inputs, pass it through a tangent function, and that generates a value between -1 and 1. And after this, then the next step will be to do layering and then to do forward propagation. So this was the hardest part of the project. It took me a long time to be able to understand how layering works and how forward propagation works, but this is how I do it. So the first layer will consist of all my sensory input, and then my second layer will consist of all neurons that depend on the sensory input, and then the third layer will be all neurons that depend on the second layer, and that will just keep on going until you have no neurons that depend on the previous layer. And what were the challenges and limitations? So at the end, I didn't have a fully working product, so the project was not complete because I didn't have the important external neurons, which tells you about the external states of the world. And also had no prior knowledge of how neural networks work. I had a hard time trying to understand layering, topological sorting, and forward propagation. So I really had a hard time trying to understand that. Um, and why this matters. So I had been meaning to do this project since high school. The first time I saw David do that video on YouTube was when I was in high school, and I've always wanted to replicate this. So now I finally had some time and I had a little bit of understanding how it worked. So I was like, let me just try and replicate it. I also proved to myself that you can do a lot in just 15 hours if you force yourself to focus. And also, it was a lot of fun to learn things under pressure where you have to just learn and apply at the same time. And what are the next steps? So, I will continue working on this project. So, this is not the end. I will have another sprint projects and I'll focus on enabling more intelligent behavior, mutation, which is important for evolution, and I'll play around with interesting ideas. So, yeah, thank you.